Okay, so yesterday we finished up right triangle trig, okay, looking at the reference angles and how you find a reference angle depending on the quadrant. And that's going to be important because when we start solving inverse equations, right, we're going to learn that there's multiple answers. Sometimes one, usually up to two. Okay? And how you find the second answer is going to depend on the reference angle and the quadrant. Okay? First, let's just talk a little bit about graphically the inverse functions. So graphically, the inverse trig functions, or the inverse of any function, it's a mirror image. What's it a mirror image of? It's a mirror image of something over the line y equals x. Kind of a simple one, an easy one I can draw. That's a logarithmic function. Okay, it curves, goes up, almost looks like it levels off. It never does, but it starts to really flatten out. There's the line y equals x. Does anybody remember what the inverse of a log is? Logarithms start to go up very, very slowly. What's the function that goes up very quickly? Yeah. Yeah, an exponential. And if I can take, you know what, let me trace over that. Okay, there's your log function. And the way I can reflect that over the line y equals x, let me see if I can try to do it. If I can't, I'll sketch it by hand.
You just rotate it.
Yeah, that's not quite what I was looking for. Let's just get rid of it. So what happens with an exponential is it goes like this. It's a mirror image of a log function. Okay? Flipped right over that line y equals x. Everyone see the mirror image there? Okay? That's exactly how you find the inverse of any function. Just mirror it. But for a function to have an inverse, it has to pass the horizontal line test. Okay? The horizontal line test says that if you draw a horizontal line, it can only hit the function once. If it hits it more than once, you do not have an inverse. Okay, so let's look at the graph of sine. If I draw a horizontal line anywhere that I want in that picture, is it possible it could hit it more than once? Yes. There's an example. Okay. In fact, in general, how many times would a horizontal line, if you drew it in some spots, how many times could it hit the sine function? Infinite. Now, if you put it up here, that's different. It wouldn't hit it at all. But let's put it somewhere that's between -1 and 1. It's going to hit it infinitely many times. Well, that's a problem. If it hits it infinitely many times, there is no inverse. So what we're going to do is, I'm going to take this picture, and we're going to kind of decide where we want to focus on. Okay? We're going to narrow down the sine function, and we're going to look at it over a certain window. Okay, so I'll keep sliding it, and you tell me when I could stop, because when you put a horizontal line in, it would never hit it more than once. Okay, how about there? No. How about there? No. Right? How about there? Yeah, right about there. Okay, it's not perfect. That's an older calculator, so it looks a little blocky. But right about there. Okay, if I drew a horizontal line in, not sure if I can draw on that. Let's see. Yeah. So no matter where I put a horizontal line in now, it's only going to hit it once. Anybody know what our window is here? It's the first tick mark to the left and to the right, if you space them using zoom 7, the normal zoom. Yeah?
Would it be negative pi over 2 to pi over 2?
Yes, it's negative pi over 2 to pi over 2. That's negative 90 to 90. There's the reason right there why inverse sine will never give you an answer higher than 90. Okay, I said that earlier, but I didn't really explain why. This is why. Okay? We have to restrict inverse sine. If we don't, there would be an infinite number of answers to every problem. Okay? We want to narrow down how many answers we have. Right? So we're only going to look at inverse sine by limiting regular sine from negative 90 to 90. Okay? Forget about everything else you can't see. Okay. So our solution, so we have an inverse, is what we just said. Restrict the domain of the sine function from negative 90 to 90. Okay, now we're going to look at the domain and range of just inverse sine, inverse cosine, and inverse tangent. I told you that an inverse function is formed by reflecting it over the line y equals x. It's basically like you switch x and y. All right? So if you had y equals 2x plus 3, and you wanted to know the inverse of that, go like this. That's the inverse. Just switch x and y. Now, if you wanted to graph it on your calculator, solve it for y again. Bring the 3 to the other side and divide by 2. So x minus 3 divided by 2, and y equals 2x plus 3, they would be mirror images over the line y equals x, because we just switched x and y. So how do you think that's going to relate to domain and range? Okay. What do you think the domain of the original function, regular sine, what do you think the domain is going to become in the inverse? It's going to be something. Which one of the two do you think it'll be? Yeah?
Does the domain become the new range?
Yeah, the domain of the original becomes the range of the inverse. Okay? Because x's and y's are switching. Okay? All your x's become y's, all your y's become x's. So your domain of the regular sine function, which we just limited because we had to, that's going to become the range of inverse sine. Now, what about the range of sine? Originally, how high and low did sine go? Think of its highest point and lowest point. What's the range of the original? Negative 1 to 1. Well, the range of the original becomes our domain of the inverse. Okay? So inverse sine is only going to go from negative 1 to 1 left and right. It's only going to go from negative pi over 2 to pi over 2 up and down. Okay, let's take a real quick look at it. So this is not a periodic function. It's not going to have infinity to negative infinity on any direction. It's just going to be a small curve right in the middle of the screen. Okay, let's, we're doing it in radians, so let's make sure we're in radians. If you wanted to do negative 90 to 90, that's fine. Then stay in degrees. Okay, so let's set our domain. Let's go negative 2 to 2. Okay, just so we don't put it right on the edge. And let's go negative pi to pi. Okay, so this will give us a good amount of room around the edges of the graph to see it. And that's it. That's your graph of inverse sine. You can almost think of it as like part of a sine wave going in a different direction. Okay, it's just part of it. And that's it. There's no asymptotes. There's no holes. There's no gaps. It's a continuous function over that domain. And you can include negative 90 and 90. That's why I use brackets. Okay? You can also include negative 1 and 1. That's why I use brackets.
How is it continuous if it stays in that?
Well, it's continuous from that point to that point. Over its domain. I'd never have to pick my pencil up to draw that. Okay, so that's inverse sine. Well, it turns out we've got to do the same thing for inverse cosine and inverse tangent. Inverse cosine, though, you can't use the same restriction, negative 90 to 90. That won't work. Let me try to sketch inverse cosine somewhat accurately. Okay, if you use negative 90 to 90, you'd be using that section right there. Does that pass the horizontal line test? Nope. So what we're going to do is we're going to look at a section a little further down. It's still going to be a window that's, if you want to think of it, 180 degrees wide. But it's going to be from 0 all the way to 180. Okay, we're going to look at that section. Okay, so 0 to pi. There's no change in the domain, because if you think about the range of regular cosine, how high and low does regular cosine go? 1 and negative 1. That range becomes our domain. And the restriction on the domain becomes our range. If we didn't restrict the domain, we couldn't do this. It wouldn't work. Okay, an inverse tangent. So tangent was a little different. So remember tangent. The original function, the range on tangent, it went up and down forever. Think of those curves. The range, it went up forever, and it went down forever. What do you have in the graph of tangent that you don't have in the graph of sine or cosine? There's something extra we have to draw. Yeah?
You have an asymptote.
What kind in tangent?
Vertical.
Vertical. So in regular tangent, you have vertical asymptotes. What do you think is going to happen in inverse tangent? Yeah?
You're gonna have horizontal asymptotes.
Yeah, you're going to have horizontal asymptotes. You're kind of going to get a graph where tangent is kind of going to be stuck in there. So remember, your vertical asymptotes for tangent were negative 90 and 90. And I put parentheses because you can't reach it. It's an asymptote, so no bracket there. But now those vertical asymptotes are going to become horizontal asymptotes. And now my graph is going to be trapped between negative 90 and 90 vertically, or horizontally. Okay? But it will go on forever in each direction, left and right. Just like regular tangent goes on forever, vertically. Okay, up and down. Okay, so any questions on the domain or ranges of those functions? All right, so we've already been using this idea. Okay, when I had you solve inverse trig functions, that inverse sine and regular sine cancel each other out, and the answer that you get is basically whatever you plugged in right there. But what I didn't tell you is they only cancel out if x is between negative 90 and positive 90. Why didn't I need to tell you that, though? Think about the kinds of angles we were dealing with when we were talking about triangles. For this equation to work, the angle has to be between negative 90 and 90. What kind of angles did you always work with in a right triangle?
You always work with either a right angle, which was 90, or less than acute angle.
Yeah, in fact, we always worked with the acute angles. Okay, so an acute angle is always between 0 and 90. Therefore, it's automatically going to be in this interval. I didn't need to tell you that. You'd never have a 130-degree angle, but try it. Try taking the inverse sine of the sine of 130. They won't cancel out. You won't get back what you started with. First, I'll try it with do it in degrees. Let's pick an angle between negative 90 and 90 and 25. Inverse sine of 25. Okay, I'm going to hit enter, and what should I get? What is it? 25, and I do. Now try it with an angle that's not between negative 90 and 90. Okay, try it with 130. Okay. Again, an angle you would never have in a right triangle, but you don't get back the same answer you started with. Okay, you get back a different answer. That's why this formula only works from negative 90 to 90. Okay, the formula below it is similar, except you're switching inverse sine and regular sine. We don't do that as much. Usually the inverse is on the outside, but it could be on the inside, depends on the problem. And this will only work between negative 1 and 1. So you could try it, try 0.5, you'll see it works. If you try a number larger than 1 and negative 1, when you plug it in, it's not even that you'll get something different back than when you started with, you'll get an error here. So if you try to take sine of inverse sine of 2, and you hit enter, it's going to say error. Okay, that won't work. The reason is, remember what we said about inverse sine. The domain of it is only numbers from negative 1 to 1. You're trying to plug in a number that doesn't exist in the domain. Okay, you're trying to do something that's impossible. Okay, so don't try to do something impossible. Okay, and then cosine has two formulas. Okay, the first one is when you have cosine on the outside. And again, same idea. Cosine, inverse cosine and cosine cancel. But this time your angle has to be between 0 and pi. Well, again, I didn't tell you this yesterday for the same reason. I guarantee you your angle is between 0 and pi in a right triangle. In fact, I guarantee you it's between 0 and 90, the acute angle. All right? So you didn't have to think about cases where, well, what if my angle is bigger than 90? No, you don't have to think about that in a right triangle. And since the domain for inverse cosine is the same as the domain for inverse sine, our restriction on this formula is exactly the same. Cosine and inverse cosine cancel each other out as long as x is between 1 and negative 1. So a question you might see, like on a test, I might write something like true or false. Is cosine of inverse cosine of 1.2 equal to 1.2? That'd be a true or false. So the first thing you do is you look, okay, inverse is on the inside. Okay, that's formula 2b. Look at x. Look at what it has to be between. Is my value between what it has to be? No, this is false. Right, so that's a very easy question. Just like a true false. Okay, and then tangent. So inverse tangent and regular tangent cancel out. And we did use this formula yesterday. As long as your angle's between negative 90 and 90, guarantee that's going to happen in a right triangle. What's different about the restriction, though, on formula 3a and formula 1a? They're both between negative 90 and 90, but there's an important difference here.
They can't be equal to the limiting values.
Right, they can't be equal to the negative 90 and 90. Now you're getting into vertical asymptotes of tangent, the undefined part. Okay, so you can't equal it. What about this one? Tangent of inverse tangent. There's two ways you can think about it. Think about how high and low does tangent go? Or think about inverse tangent, how far left and right does it go? Yeah, there's no restriction on this one. So this formula always works. Okay, So there's 6 formulas that tell you when the trig functions cancel each other out. In a right triangle, you don't really have to think about the restrictions. In other cases, you do. I'm not going to get into really graphing too much with inverse trig functions, but I want you to know all the transformations we've studied multiple times all work the same. Okay. What I might do is give you an example and just say, tell me the steps. You'd stretch it, shift it, compress it, something like that. Okay, but A is your horizontal shift, B is your horizontal stretch or compression. A and B do the opposite of what you'd expect. C is a vertical stretch, D is a vertical shift. C and D do exactly what you would expect. Okay, so I'm not going to waste any more time talking about that. Okay, so one thing that we do want to know how to do, though, is if we do a transformation, how do you find the new domain and range? Well, to find the new domain of an inverse trig function, you're going to create a compound inequality. Okay, that's when you have something here, something here, something there. So you're going to create a compound inequality, and in the middle, right there, you're going to put your argument. Okay, whatever the argument happens to be. Because remember, A and B affect the horizontal. C and D affect the vertical. I don't care if you vertically stretch something. That doesn't do anything to the domain. If you shift something up or down, that does nothing to the domain. That's range, but that's not domain. So you put your argument in the middle, and then you put your original domain on the left and on the right. What do I mean by the original domain? Well, go back to your sheet where we just listed domain and range of all the trig functions, if you don't remember. And then we solve it. Okay, so we'll try a couple examples. And then how do you find the range? Well, that's what C and D affect. Let's say the range originally was from, let's say, just to use an easy number, you had a range from 3 to -3, and you did a vertical stretch by a factor of 2. Well, now your range doesn't go from 3 to -3, it goes from 6 to -6. You just doubled it. Okay, let's say you shifted something up 1. If you had a range that was -3 to 3, and you shifted up 1, now it's going to go from -2 to 4. Each number gets shifted up 1. Okay, so we always do the stretch shrink first, and then we'll deal with shifting up and down. Okay, so I don't want to sketch it. All I want to do here is find the new domain and range. Okay, so step 1, find the domain. Create a compound inequality, put the argument in the middle. That's the argument, 2x. Put the original domain on the left and on the right. What was the original domain of inverse sine? Think about how far left and right it goes.
-1 to 1.
Okay, let's just double check. So original domain, perfect. -1 to 1. So we're going to put those two numbers down. -1. 1, could it actually hit those values? Yep. So then put in the equal to's. And now solve for x. And we're done. Divide by 2, divide by 2, divide by 2. So now x is going to be between -0.5 and 0.5. That's it. Did I do anything to change the range there? Nope. So what's my range going to stay at? Or in other words, what's the range before you do anything to it?
Negative 1 to 1.
Well, that was our domain, negative 1 to 1.
Oh, I'm sorry. Negative infinity to infinity.
So the only ones that have the infinities are something to do with tangent.
Oh, we're focusing on the little one, right? So it would be negative pi over 2 to pi over 2.
Yeah, negative pi over 2 to pi over 2. Okay, I'm going to skip B. All B would do essentially, I'll tell you the answer, it's going to make it negative 3 to 3. It's going to triple. It's going to stretch. Smaller numbers inside make it bigger. So your domain would become negative 3 to 3. No change in the range on that one. Let's do one that's a little more interesting. Okay, let's try this. What's the domain going to be in C? Nick?
Negative 1 to 1.
Yeah, we haven't done anything to the domain. The only things that would affect the domain is if you had something in the parentheses. There's nothing there. There's no A, there's no B. There's only a D. Okay, that's a vertical. Affects the vertical. So negative 1 to 1. Okay, now my range. Let's start with what the range is originally. What's the original range for sine? Negative pi over 2 to pi over 2. Now, there's no nice way to write this answer. You're shifting both of these values up 2. So what I would do is just write negative pi over 2 plus 2 to pi over 2 plus 2. Now, you could find a common denominator if you wanted to and add them up, but it's still not going to be a terribly nice number. Okay? If you did find a common denominator, it would be pi plus 4 over 2. Still, doesn't really look that much better than what we have there. Okay, so I'll leave it like that. But keep in mind in the book, they may write it with a common denominator. Okay? I don't think you'll see it with a decimal, usually, unless they ask for it, but don't worry about the decimal. Let's see. Let's try one with tangent. Okay, just as a hint on D, there's no change in the domain. You've done nothing to it. Okay, but let's look at E. Okay, so I'm going to start by putting my argument in the middle. What's my domain of tangent? The original. Think of the inverse function. Think about how far left and right that graph goes. Josh? Yeah, it's negative infinity to infinity. And we're going to divide by 2. Not negative 2, sorry. So how far left and right is my graph going to go now?
Negative infinity to infinity.
Yeah. When a graph goes from negative infinity to infinity, you can't change that. You can stretch it, you can compress it, you can shift it, but it's still negative infinity to infinity. Okay, and now my range. What's the range of inverse tangent before you do anything to it? And if you get stuck, think about where the horizontal asymptotes would be. Yeah?
Negative pi over 2 pi over 2.
It would be negative pi over 2 to pi over 2. Now you've tripled it. Negative 3 pi over 2. And it's an asymptote. You never reach it. To 3 pi over 2. Now, let's say I'm not going to write this down, but let's say you had this down. Now all I do is this. First, I would handle my stretching up and down by tripling. And then I would add 1 onto the end. Okay. I just wanted to show you a problem that had both in it. This one doesn't. Okay. Any question on how we got negative 3 pi over 2 to 3 pi over 2? Okay, so it's not bad. As long as you remember the originals, you can always make a cheat sheet for a test. So you don't have to memorize that. Okay, this one I want to know the transformations from that to get that. It's going to be 4. Okay, I don't like the way the book wrote this problem, though. There's something I would do here before I even start listing the transformations. It's not in the standard form that we normally have, the A, B, C, D. It's not written that way. Did anybody see what I'd have to do to make it written that way? One small thing.
Distribute the 1/4.
Just distribute the 1/4. Okay, so what we'll do is write it as 1/4 x plus 2. Now I can see shifting, stretching or compressing, all that stuff. Okay, who can tell me the first thing we would do to change inverse sine x into what's up above? What's the first transformation? Marina?
It would be shifting left 2.
Shift left 2. Yep. Okay, who can tell me the next thing? There's two, and there's really two ways you could say it. Yeah, John. Okay, that is one way to say it. You can vertically stretch by a number less than 1. So that's fine. Sorry, did you say vertical?
Oh.
Horizontal. Yeah. So it's a horizontal stretch by a factor of 1/4. What's another way to say that? Instead of saying stretching by 1/4.
You're compressing it by a factor of 4.
Compressing by a factor of 4. Could say that too. All right. Step 3, that's a vertical stretch. And that is by a factor of 3. 3 times as tall. Okay, and Taylor, how about the minus 5 at the end?
You'd be shifting it down 5.
Shift down 5. Okay, so shift down 5. Any questions on listing out your transformations? Not much new there that we haven't really done before. Okay, and then the last part, yeah, solving on the calculator. All right, so what we want to do is, first of all, let's see, the book, if they want us to restrict our answer. All right, let's see if we can find inverse sine of 0.5. Okay, there's a few ways you could do it. Okay, and I'm not really going to be picky about how you do it. You could graph inverse sine of x. You could graph the line, graph something else, and then see where they cross. Okay? You could do it that way. So this question is basically saying this. The sine of what angle would give you 0.5? If you were going to graph it, that's how you'd have to do it. What angle do you take the sine of and get 0.5 as the answer? All right, so let's, instead of graphing it, I think let's just type it in by using the inverse sine function. What do we know that I'm going to get for an answer? It's going to automatically be between what two angles? What's the domain of inverse sine? Sorry, the range I'm looking for. But not 0 and 90. Close. Yep. Negative 90 to 90. So when you type in an answer here, you're going to get something between negative 90 and 90. And we know that. Okay, let's see what we get. So second inverse sine of 0.5. Get 30. And anytime you do inverse trig, the answer is an angle. Now, I want to show you something that's going to be important. The book is only focusing on one answer here. But if I graph sine of theta in y1 and I graph 0.5 in y2, watch what happens. Sine of x, 0.5. Let's do it in degrees and we're all set. Okay. All I really want to do is focus on 0 to 360. Okay. Forget everything else. Okay, let's do second calc intersect at that first point. See what we get. Actually, that already told me. 30. Okay, we just got one of our answers. The sine of what angle is 0.5? 30. But there's another answer. Well, this diagram can help you to get the second answer. Okay. In quadrant 1, all of the trig functions come out positive. Right? You were looking for a value. 0.5 is a positive value. All the trig functions, you're going to have an answer in quadrant 1, whether you do inverse sine, inverse cosine, or inverse tangent. They all come out positive in quadrant 1. In quadrant 2, right, the only trig functions that come out positive are the sine values. Sine of 100, sine of 120, sine of 150, sine of 170. They're all going to be positive numbers. Anything else in that quadrant is negative. Cosine of 100, negative. Tangent of 110, negative. Tangent of 179, negative. Okay? Sine is the only ones that come out positive in quadrant 2. In quadrant 3, the only trig functions that come out positive are tangent. Tangent of 200, tangent of 210, tangent of 269. They're all going to come out positive. Okay? Sine of 200, negative. Cosine of 200, negative. Okay? Tangent is the only trig function that's positive in quadrant 3. And what do you think the C stands for? Cosine. In quadrant 4, cosine is the only trig function that comes out positive. Cosine of 350, cosine of 290, okay? Things like that. So, we're dealing with sine, and we got an answer in quadrant 1. What's the other quadrant that sine could also come out positive in, besides quadrant 1? Quadrant 2. I want you to think of this 30 degrees as a reference angle. If 30 degrees was your reference angle, what would be the answer in quadrant 2? Think of your formula for what you do with the reference angle. It has the 180. Just remember if it's plus or minus.
50 degrees.
150. So if you did 180 minus your reference angle, you get 150. Let's look at the other intersection point. Second calc, intersect. 150. There's your other answer. Okay. So the idea is you use your calculator to get one answer. Use this diagram and say, okay, well, did I have a positive? Did I have a negative? And find the other quadrant where it's positive or negative. Okay, so let's try this one. Okay, inverse sine of negative 0.7. Well, let me use my calculator to get one answer. Second, inverse sine, negative 0.7. Now I know I'm going to get an answer between negative 90 and 90. I already know that. In this case, I knew it wasn't going to be between 0 and 90 because that would have been positive, quadrant 1. Okay, so I knew it's going to be negative. So negative 44.4. Let's just say that. Okay, that's one answer. So the way you want to think of this, the sine of what angle is going to give you negative 0.7? Well, we have one answer. The sine of negative 44 will give you negative 0.7. Which other quadrant? Okay, you just got an answer there. Which other quadrant is sine negative in? Yeah? 3. Quadrant 3. What's your formula for finding the other answer in quadrant 3? Take your reference angle and do what with it?
Add 180.
Add 180. Remember, I always want you to think of your reference angle as a positive. 224.4. If you're not sure, check your answer. Take 224.4, take the sine of it. Look what you get, negative 0.7. Take negative 44.4. Take the sine of it. Look what you get, negative 0.7. Okay? So I'm showing you how to get that other answer, which the book doesn't show you, but if I don't show you now, I have to show you later. So since we're doing half the problem, might as well show you the whole thing. This is basically saying the sine of what angle would equal 1.2. When does your graph of sine hit 1.2? Josh? It doesn't. The graph of sine never goes that high. You're trying to solve this problem. Tell me where those two lines cross. They don't. There's no solution there. Okay, so it takes a little bit of work kind of learning how to get one answer, figure out the quadrant for where you want your other answer, and then using those formulas. Okay, now I know it's quadrant 2, it's 180 minus. Quadrant 3, 180 plus, and so on. Okay, but we'll be practicing that throughout this whole chapter. All right, so the homework's on 394. 1 to 9, 13 to 20, 20 to 24, and 27 to 33. You can use a calculator for most of it. I don't think you'll need a graphing one, but you will need a scientific one.